Welcome to this explainer. Okay, today we are going to dive straight into the fascinating engineering that makes everyday wireless communication possible. I mean, it's pretty wild to think that completely invisible waves dictate nearly every aspect of our modern lives, right? If you've ever, say, tuned a radio dial or wondered how a broadcast tower reaches your car miles away on the highway, well, you're about to see the exact mechanics behind it. So, how exactly does a human voice travel invisibly through the air? Before we get lost in the math and the specific circuits, we really need to frame long distance communication as a physical puzzle that needs solving. Because, it isn't magic, it's actually a super careful manipulation of energy. To keep us on track, here's our roadmap for today. First, we'll cover the basics of communication. Second, why we actually need modulation. Third, we'll look inside amplitude modulation. Fourth, the power of AM. And finally, sending and receiving AM.
Section 1, the basics of communication, mapping the system.
Let's start with a high-level map. Our journey begins with a signal moving from a source right into a transmitter. That transmitter's job? To couple our message into a high-frequency signal so it can survive the long trip ahead. Then it travels through the channel. That's the physical medium, like the air around us. But notice what crashes the party here. Noise. The channel is exactly where unwanted interference creeps in. Finally, the signal hits the receiver, whose sole job is to demodulate that signal, essentially stripping away all those high frequencies to deliver the pristine original message to its destination. Section 2, why we need modulation, solving the transmission problem. You see, we can't just throw raw audio into the air and expect it to go anywhere. Baseband signals, like our voices, are just completely incompatible for direct transmission over any real distance. So, enter our hero, modulation. Technically speaking, this is the process of shifting the frequency spectrum of a signal to a range where we can achieve more efficient transmission. It is the elegant solution to our big transmission problem. We're basically taking low-frequency information and piggybacking it onto a high-frequency carrier wave that actually can make the trip. To put this into perspective, without modulation, trying to broadcast a raw audio signal would require an impossibly massive antenna, literally miles high. But by translating these frequencies, we can use antennas of a normal, manageable size. Plus, modulation performs a bunch of other absolutely vital functions. We get what's called frequency multiplexing, which is a fancy way of saying multiple signals can share the exact same channel without jumbling together in the air. It essentially gives us highly efficient transmission while seriously reducing noise and interference, a total game changer. Section 3, inside amplitude modulation, the envelope analogy. So amplitude modulation, or AM for short, is the process of changing the amplitude of a high-frequency carrier signal so it perfectly matches the modulating signal, the actual information. In the real world, this typically operates in the band between 535 and 1600 kilohertz. But the absolute vital takeaway here is that in AM, the actual frequency of the carrier wave isn't affected at all. It stays entirely constant. Only its height, its amplitude, changes linearly to match our audio. Think of the baseband signal as a slow, rolling wave of someone talking. When we combine them, you get this incredibly fast carrier wave being squeezed and expanded. Notice how its outer boundary, what we call the envelope, traces the exact shape of that original slow message signal. So, the high-frequency carrier acts as the envelope, and the baseband signal is the letter safely tucked inside. Now, engineers have to look at this exact same wave in two completely different ways to fully understand it: the time domain versus the frequency domain. In the time domain, we're visualizing how the waveform's amplitude fluctuates over continuous time. It's like watching a real-time heartbeat. But in the frequency domain, we stop looking at time entirely. Instead, we visualize where the signal's power peaks across the spectrum, representing delta functions at specific frequencies. Both of these views are 100% essential to actually designing these systems. Section 4, the power of AM. Where does the energy go? Okay, let's move past just the shape of the wave and look at the physical reality of how power is distributed within it once it actually leaves the transmitter. When looking at the power relations in an AM wave, we really want to focus on the total power equation. It sums up three distinct components: the power of the carrier wave itself, the power of the lower sideband, and the power of the upper sideband. These three elements combine to give us the total average energy blasting out of the antenna. Visually, that total energy is split strictly between the carrier wave and the sidebands. But here is the truly fascinating part. The carrier itself contains exactly 0 of the original message. No way, right? All of the actual information, your voice, the music, whatever it is, resides entirely within those two much smaller sidebands. The carrier is really just a high-powered vehicle doing all the heavy lifting to push those sidebands through the air. Section 5. Sending and receiving AM. Circuits in action. All right, let's translate this math into actual hardware. At the transmitter stage, we need to generate this AM wave using a switching modulator. It essentially uses a semiconductor diode as an ideal switch. We apply the carrier signal and the information signal at the exact same time. When that high-amplitude carrier is positive, the diode is forward biased. It acts like a closed switch. When it goes negative, the diode is reverse biased, acting like an open switch. This rapid periodic switching effectively multiplies our message with the carrier. Boom, we have our AM wave, which is then nicely smoothed out by a bandpass filter. On the flip side of the receiver, well, we have to get that message back out, right? To do this, we use a beautifully simple circuit found in almost all commercial AM radios, the envelope detector. Its entire job is to rip open that high-frequency carrier envelope we just created and extract the low-frequency letter inside. Let's walk through how this elegantly simple setup works. As the incoming wave hits, the diode forward biases on the positive half of the cycle. This causes the capacitor to charge up incredibly rapidly to the peak voltage of that high-frequency wave. But as the input wave starts to drop from its peak, the diode reverse biases, basically turning off. With the diode off, the capacitor starts to discharge, but it does so very slowly through the load resistor. By charging super fast on every peak and discharging slowly enough to bridge the gap, the circuit literally traces out that original slow message signal. As the theory goes, the result is that the capacitor voltage, or the detector output, is nearly the same as the envelope of the AM wave. By properly timing that discharge cycle, using just a simple resistor and a capacitor, the receiver successfully extracts your low-frequency audio right out of that invisible high-frequency carrier wave. It's just brilliant. And that brings us to a really fascinating final thought for this explainer. If a beautifully simple resistor-capacitor circuit can effectively decode these analog radio waves traveling for miles and miles through the thin air, what kind of incredible hardware is required to lock onto the complex digital phase shifts of modern Wi-Fi or 5G? While amplitude modulation represents the fundamental bedrock of wireless transmission, seeing how it elegantly solves the problem of distance makes you truly wonder just how advanced the invisible pathways of our modern digital world have actually become. Thanks so much for joining me today. Keep learning, and I'll see you next time.